In this video, we're going to look at confidence intervals. We're going to calculate and interpret a confidence interval for estimating a population mean and a population proportion. We're going to use a student T's probability distribution as the sample size changes. We're going to discriminate between when we use the normal versus student T's distribution. We're going to calculate the sample size required to estimate a population mean and a population proportion, given the desired confidence level and the desired margin of error. So in chapter 7, the central limit theorem, we were able to make inferences from samples of non-normal populations, and that was because as we do a lot of samples of repeating the same type of experiment, and sample sizes of 30 or more, we found that if we take the means and plot those, we end up with something that is normal. This theorem, the central limit theorem, allows us to assume that given large enough samples, the sampling distribution will be normally distributed. And the result is that normal, or that random variable, which is the capital X and with a bar, is normally distributed with a given population mean and a given standard deviation, which is the sigma that was given to us divided by the sample size. When the population standard deviation sigma is known, we use a normal distribution to calculate the error bound. So far, we have used sample data to make generalizations about an unknown population. This part is called inferential statistics. So what we've been doing is inferential statistics. The sample data allows us to estimate the population parameter. The sample mean, which is lowercase x bar, is called the point estimate for the population mean, mu. Now remember, x bar is called a statistic and it comes from the sample, and mu is called a parameter and it is in reference to the population. The point estimate is not an exact value of the population parameter as much as we try it to be, but we are hoping that it's going to be close to it, and the way that we try to make it as close to it as possible is constructing an interval which will estimate where it ought to be, the population parameter ought to be, and we call this a confidence interval. The interval is a number range in which we have a calculated mean for the sample, and then we assume that it should be within this range, and we're going to calculate these data numbers that give us our confidence interval based on our confidence level that we are hoping for. The confidence interval is likely, fingers crossed, to include the unknown population parameter that we are chasing. In this chapter, we learn about confidence intervals in general, which provides you with a way of estimating population parameters, because it is highly unlikely, like probability of 0, that your sample statistic is going to match the population parameter. So we say, well, we're pretty confident in this region of numbers. So instead of just giving us a one number estimate, we give us an interval of numbers that's likely to be in. This is useful because, like I said, the probability of us getting a sample statistic to match exactly the population parameter is 0. So the distribution that we are looking at, so here's a nice normal distribution, and say here's where the population parameter is in. So we find this confidence interval that we hope grabs this population parameter, and so we find this x bar, and then we talk about the confidence interval. How do we find this confidence interval? Well, there's multiple ways. The first one is supposedly we know sigma, but here's the thing. If we know sigma, we know which is a parameter, we would know the mean, which is the mu. So it's unlikely that this would ever really happen, but we do need to talk about it because it shows up in the homework, and it could happen, but again, the probability is so low, like close to 0. We're going to need to estimate x bar we're going to need to use x bar as an estimate for mu, which is the population parameter. So we're going to need this margin of error. So this EBM is called the error bound for a population mean, also abbreviated as EBM. This sometimes refers to as the margin of error. The sample x bar is the mean. It's a point estimate of an unknown population mean, mu. The margin of error depends on the confidence level that we are interested in. The confidence level is a level, like a number, like we're 95% confident. That's a confidence level. So that is the confidence level. That is not the confidence interval, but we do need the confidence level to figure out what the confidence interval is. The way in which we do this is we are going to take our point estimate, which is going to be x bar. We're going to subtract off the error bound. That's going to give us our lower part of the interval, the starting part of our interval. And then we take our point estimate, which is x bar, and we're going to add to it the error bound, and that's going to give us our upper part of that interval. We choose an EBM so that we can say something like we are 95% confident or certain that this confidence interval contains the true population parameter, or if we're looking for means, of the population mean. More accurately, we could say 95% of the samples of this size from the population produce confidence intervals that contain the true value of the population parameter. Now remember, we are taking samples and we are using those samples to estimate the population. Conversely, we could also say that 5% of the samples of this size from the population produce confidence intervals that do not contain the true value of the population parameter. So this 5% is known as the alpha, and the alpha is equal to 1 minus the confidence level, and these are all as percents. And this is the probability that our confidence interval does not contain the true value of the population parameter. Note that confidence level and alpha are both probabilities, and they need to be expressed as decimals or as a percent. Typically, we'll take the percent and turn it into a decimal. More often than not, the choice is a 90% confidence level or higher, because we want to be reasonably certain that my conclusion is true. So here's two examples in which when I increase the confidence level, how my spread of the data increases. Here's 90%. So I'm 90% confident. Notice I'd turn that into a decimal, so 0.9. And then I have 0.5, which means this tail is half of that and this tail is the other half. If I have a 95% confident, that means that I have 0.5. So I split it in half. So the way in which we construct and interpret the confidence level is, first of all, we'll need to know a mean. And supposedly we'll always know sigma in this part of the homework and this part of the video. It's highly unlikely that's ever going to happen. We need to find a z-score. Then from the z-score, we're going to calculate the EBM, the error bound. We'll construct the confidence interval. And then we're going to write some sort of sentence that interprets what we've got. So to find the z-score, we're going to use a standard normal distribution. So we know with the standard normal, n has a mean of 0 and a standard deviation of 1. Since the confidence level is the area in the middle, then we are, of course, going to use alpha divided by 2 because of the tails. So the z-score is actually a z alpha divided by 2 score, so we label it z alpha divided by 2. We'll use our spreadsheets to find that z-score, and the way that we will do that is norm.invert, and then we will put in our alpha divided by 2, 0 and 1. Because the mean is 0, the standard deviation is 1. You can also, by the way, to find your z-score, you can use the norm.s.invert. And in this case, you'll just use your alpha divided by 2. I'll show you the spreadsheet that you're going to use to calculate all of that. Once we find that z-score, then we find our EBM as doing that z-score that we just found multiplied by the sigma that'll be given to us divided by the standard deviation. Or excuse me, the square root of the sample size. Man. So here is our first example. A standard deviation of the weight of elephants is known to be approximately 15 pounds. That's our sigma. We wish to construct a 95% confidence interval for the mean of newborn elephant calves. 50 newborn elephants were weighed. The sample mean was 244. The sample standard deviation is 11. So we now have the X bar, which is 244 pounds. The sigma is the 15 pounds. The N is 50 elephants, and notice I don't actually care that much about the 11 pounds at this moment. So what is X and X bar? Well, the capital X is going to be, and that's our random variable, is the weight in pounds, weight in pounds of newborn elephants spelling is not my forte. And then the X bar, again, is a random variable and is the average weight of the sample. So X bar is sample, X without the bar is for the population. So this is going to be the average weight in pounds of the newborn elephants from the sample. And we have a sample of 50. So a sample of 50. Okay. Which distribution should we use? Well, we are going to use a normal distribution. And so it's a normal, and 244 will be the mean that I'm going to use. I'm going to use my sigma, which is 15, divided by the square root of n, which is 50. So that's my standard normal. I am going to construct a confidence interval of 95%. So I'm going to use my spreadsheet, and from my spreadsheet, I'm going to be able to tell you what those numbers are. So give me a moment. Let me finish this off. I will give you the numbers now, and then we'll go over how to find this in the spreadsheet. Now, here is where my X bar is, which is 244. If I go and calculate my EBM, which is going to be my X bar minus my EBM, and my X bar plus my EBM is going to be giving me confidence interval values. My EBM is going to be my Z-score. I'm going to actually do the absolute value of my Z-score, which we'll calculate, multiplied by my sigma, divided by, so my sigma, which is 15, divided by my n, which is 50. Okay, so it's really the Z-score that I'm chasing. And then I'm going to show you the calculator, but I put in my calculator, and my lower bound is going to be 239.84, and my upper bound is going to be 248.16. So this is what I get. So my error bound that I got, my EBM using my spreadsheet, which again I'll show you in just a moment, is 4.1577. And so I would add and subtract that value from the 244. That's where I got those two numbers. So the confidence, this is where I'm 95% confident. So this is the 95%. I'm going in this direction. I go in this direction. That's where I expect the population of the average weights of elephants to be newborn elephants. So write a sentence that interprets this estimate, and I would say something like, we are 95% confident that the mean weight of newborn elephant calves to be between 239.84 pounds and 248.16 pounds. So that would be the sentence I'd write there. What will happen at the confidence interval if we have 50 newborn elephants instead of 50? Well, as a sample size increases, there'll be less variability in the mean, so our interval size will decrease. So once I show you the spreadsheet, if you put in 500 instead of 50, you'll notice that my numbers 239 actually goes down. It goes down to 242. So that's, kind of a squeeze. I'm getting closer to 244, even closer to 244. So here's the spreadsheet I was talking about. So you're going to have CL as the confidence level. Alpha is going to be 1 minus the confidence level, and then alpha divided by 2, because we're splitting this into two tails. So that's why we do the alpha divided by 2. A z-score is going to be negative, is going to be below the mean. A z-score that's positive means we're above the mean. The EBM is going to be the margin of error, which is going to be my z-score alpha divided by 2. I'm not going to take my z-score alpha and then divide it by 2. This is the notation, the z. This is the notation, z alpha divided by 2. That's what that is. In fact, everywhere I see the z alpha divided by 2, that is just the notation. And then I'm going to multiply that by the given sigma and then divide by the square root of the sample size. So n is this number of trials or data pieces, x bar is a sample mean, ci is the lower limit of the confidence interval, so ci lower limit, and ci upper limit, so that is the left and right side of the confidence interval. And the z-score is the number of deviations the value is from the mean. We call this the critical value in this chapter. So if they ask you for the critical value, they're asking you for the z-score. So I enter the confidence level. I'm going to enter my number of data of pieces. If I have an x bar other than 0, I'm going to put that in here. And then I'm going to put in the sigma other than 1. So then I have alpha. This alpha is going to be 1 minus my confidence level. Notice my confidence level is 0.95. And then this alpha divided by 2 is literally, I'm going to take this cell and divide by 2, so that's here. I'm going to use a norm.invert, so I grab the cell that has the alpha divided by 2, 0, and 1. I can, of course, also, so I can say or, I can use the norm.invert, or norm.s.invert, and just have the one that has a z alpha divided by 2, and that's all I need to do. Now, here I chose 0 and 1 because I have the norm.invert and not the norm.s. I mean, if I'm using the norm.s, I would just need the z alpha divided by 2. What is this? And this kind of makes sense because I'm looking at this. This is my, you want to think about this as my probability or my percent. So that's what that is on the left tail. So the z-score then would be negative because I'm below. And that means on my EBM, I need to multiply. Actually, I need to find the absolute value of that because I need to add and subtract. So I take the ABS. So in this cell, I type in equals ABS. I'm going to grab the cell that has my z-score. It's z, and that really is the z-score of alpha divided by 2. Multiply that by sigma and then divide by the square root of n. And so I get this. And then I do my x bar minus my EBM, so I grab my x bar. I'm going to subtract off that EBM and my x bar plus my EBM, and so this is going to give me my upper and lower values on my confidence interval. If we are working backwards to find the error bound or the sample mean or the sample size and sigma is known, then from the upper value of the interval, we're going to subtract the sample mean. Or from the upper value of the interval, subtract the lower mean and then divide by 2. So if we don't have the mean, we just take the upper minus lower, divide by 2, and that's going to give us our sample mean. So if I need the sample mean, again, subtract the upper and lower, divide by 2. So that's how I find the sample mean. Since there are two ways to calculate these, choose one that is the easiest for you. Because we know that the EBM is equal to the z-score of alpha divided by 2 multiplied by sigma divided by the square root of n, if I divide both sides by the EBN, so that's why this is down here, I'm going to multiply both sides by the square root of n, that's why n comes over here, and then I square both sides to get rid of the square root. This is what I get. I get this formula, which is basically going to be z alpha divided by 2 times sigma EBM, and then there should be a squared right there. So z alpha divided by 2 times my sigma divided by my EBM squared is going to tell me the sample size. Suppose we know a confidence interval is 42.12 to 47.88, and we want to find the error bound and the sample mean. So what we're going to do is we're going to take the upper minus the lower, so upper, which is the 47.88. I'm going to minus the lower, which is 42.12, and I'm going to divide by 2, And this is going to give me my sample mean. So this is my X bar, okay? So assuming that I did this on my spreadsheet, which I'll show you in just a moment, I'm going to get, in this case, 45, okay? So if I have 45, then my EBM is going to be 47.88 minus that 45. And so my EBM is going to be 2.88. This is my EBM. Now, the population standard deviation for the height of high school basketball players is 3 inches. If we want a 95% confidence level that the sample mean height is within 2 inches of the true population, how many randomly selected students do I need to survey? So my N is going to be equal to, well, I'm going to have to find my Z alpha divided by 2. So if my confidence level is 0.95, then I'm going to have a an alpha is going to, divided by 2, is going to be 1 minus 0.95 divided by 2. And then I would use my spreadsheet to find my Z-score. And for my Z-score, it's going to end up being, it's going to be a negative, but I'm going to square it so it doesn't matter. So I'm going to have 1.996. It's going to be multiplied by my sigma, which is what, 3 inches? 3 inches. And then I want to be within 2 inches, so I'm going to take all of that and square it. I'm going to actually have a calculator to do that, so let me show you what that looks like. And in my calculator, I end up with 35. So let me show you what calculator I'm using. So if you know the lower limit, you're going to enter it. If you know the upper limit, you're going to enter it. If you know the sigma, you're going to enter it. And then if you know the Z-score, you're going to enter it. Now the Z-score comes from up above, just using the alpha divided by 2. So what I mean by up above is the other calculator. This will give me my Z-score, or T-score if that's it. My EBM, in this case, is going to be calculated for me. My X-bar will be calculated for me. If you need to calculate the EBM first, which I don't, then this is what I would use. If I don't need to calculate the EBM, in this example I didn't, I needed to be within 1, so I'd put in 1 here, and then this would calculate this. Now, this is different than the 35 because these numbers up here are different. So this is what I would use to find my sample size if I knew my EBM, if I knew my sample mean, and sigma is known or unknown. It doesn't actually matter. Now, what we have most of the time is we have no idea what the population standard deviation is. That's what happens most of the time. So we use something called the student's T distribution, and this is what I found out when I was randomly looking at something else. This actually comes from the student T distributions, comes from a statistician who didn't want his name associated to it. And the statistician actually worked for Guinness, like Guinness the beer. So this is where it comes from. It's a really little tidbit of useless information. You can thank Guinness beer for the student T distribution because that's who the statistician worked for. Anyways, that's why it's called student T. When we're using this, we are going to be needing to find degrees of freedom. So this degrees of freedom is going to be the sample size minus 1. And the reason we do this is that it adjusts for any kind of slight discrepancies we may have when we don't have sigma. The student T distribution here is going to be now finding a T-score instead of a Z-score. We call this the critical value. It's going to be calculated the same as if we had the Z-score. It's going to be the X-bar minus mu divided by S. Now we're going to use the sample standard deviation, and then we divide by N. The EBM is calculated as the T alpha divided by 2, S, and then the square root of N. And again, X-bar plus and minus the EBM. Couple of things about the student T distribution. It's similar to the normal curve. The mean for the student T distribution is 0, and the distribution is symmetric about 0. The student T distribution has a probability in its tails that are slightly larger than the standard normal distribution because the spread of the T distribution is greater than the standard normal. The exact shape of the t distribution depends on the degrees of freedom. There are some assumptions that come along with a student t distribution. Is that the data that we're selecting is random sampling. The mean of the population is mu. There has to be at least 30 pieces of data. Or the population needs to follow a normal distribution, and there will be no outliers in the data, and the population standard sigma is unknown. So here is what a standard normal distribution is. It's really kind of skinny thing here. This is a t distribution where n is close to 30, that's this red, and this is a t distribution where n is less than 30, so you can see that it's not really a good choice for using a t distribution. A hospital is trying to cut down on the emergency room wait times, is interested in the amount of time parents must wait before being called back to be examined. Patients, not parents, patients. An investigation committee randomly surveyed 70 students. The sample mean was 1.5 with a sample standard deviation of 0.5. So let's go ahead and scroll in. X bar, well, that's the sample mean of 1.5. The sample standard deviation is 0.5. My n is 70, so my degrees of freedom is 70 minus 1, so 69. In words, define what the random variable x, capital X is, and X bar. Well, capital X, the random variable, is the expected wait time in an emergency room for this particular hospital. X bar would be the expected wait time for the sample at this particular hospital before the patient is being seen. Which distribution? Well, we know this is the student t, because we don't have sigma. So student t. Construct a 95% confidence for the population mean of the newborn elephants. That is not right. It would be constructing a 95% confidence for the mean wait or expected wait time in this emergency room before being seen. So once again, I'm going to give you numbers, and then I'll show you the calculator, the Excel spreadsheet that I use to do the calculations. So this is where the 1.5 is. Calculating my EBM. My EBM ended up being 0.12. That means we're going to come down to 1.38. And we're going to go up to 1.62. So my confidence interval is 1.38, comma 1.62. So that is about what we expect to wait at this particular hospital. So write a sentence that interprets and estimates the contents in this situation. We are 95% confident that the population mean waiting time is between 1.3 hours and 1.62 hours for the patient to wait before being called back in the emergency room of this particular hospital. And then, of course, what happens if we do 50 instead of 70? It, of course, shrinks the confidence interval. It makes these confidence intervals numbers that are closer to the 1.5. So that's what that does. And this is what the calculator that I would recommend you have that you'll need for this section. CL is confidence interval as before. Alpha divided by 2 is splitting this into two tails. EBM is the same. This time we're going to do the T alpha divided by 2. And this is the notation of T alpha divided by 2. It doesn't mean you take your T-score and divide it by 2. It is the notation. Multiply it by your standard deviation for the sample, and then the square root of n. And I end up with all of this. And so I'm going to use a t distribution, which means I need degrees of freedom. Confidence level, my n, my x bar, my s. My degrees of freedom is going to be 26 minus 1. Here's my alpha divided by 2. Now I use t dot invert. I'll need the alpha divided by 2. This is not taking the alpha and divided by 2. This is taking this cell, which is alpha divided by 2, and then the degrees of freedom. Then I take, of course, the absolute value of the t-score, multiply by s, divided by the square root of n, and then I have my error bounds for either one. Now the last part of this is when we have proportions. So we've talked about having sigma known, sigma unknown, and now what happens if we're giving stuff in terms of proportions. If we're given stuff in terms of proportion, there's no mention of a mean or average. They might say, 52% of the population does this. Then we use the binomial distribution where we have n and p, where n is the number of trials and p is the percent of success, the probability of success. So p hat is going to be the success divided by n. P hat is sometimes referred to, a capital P hat, sometimes referred to as p prime. When n is large and p is not close to 0 and 1, we can use the normal distribution to approximate the binomial. So this x could be randomly as a normal distribution if we have a large n. My mean would be n times p, and my sigma, or my standard deviation, would be the square root of npq. Again, this is nothing different than what we did in chapter 7, and p is success, q is 1 minus success, or the failure. Now we have an EBP, which is the error bound for proportion. Now, we have this random variable x, which is normally distributed in times p is our mean, and then the square root of npq. But since p hat is equal to p prime, which is equal to our random variable x divided by n, then p hat would be the normal distribution, dividing this by n and dividing this by n, becomes just p, comma, the square root of n, or pq divided by the square root of n. So our z-score is a little bit easier, so we have p hat minus p, square root of p times q divided by n, and we have the EBP, which is error bound for proportion. Confidence interval has our p prime plus our EBP, p prime plus and minus our EBP. A couple things, the confidence interval can only be used if the number of successes and the number of failures, so NP prime is greater than 5 and NQ prime is greater than 5. So let's take a look at our example here. We have 1,050 randomly selected adults. 360 identify themselves as manual laborers. 280 identify themselves as non-manual wage earners. 250 identify themselves as mid-level managers. 160 identify themselves as executives. In the survey, 82% of the manual laborers preferred trucks, 62% of the non-manual wage earners preferred trucks, and 54% of the mid-level managers preferred trucks, and 26% of the executives preferred trucks. So if we need to identify the p hat and q hat and n, I need to decide what is it that I'm looking at. Am I looking at the p hat being non-manual wage earners, manual laborers, mid-level managers, or the truck preferences? So let's go ahead and just pick one. Let's do the 26% of executives prefer trucks. So that's what we're going to use as our p hat. Success is choosing to like trucks for the executives. Could have chose anything, but it's a last sentence, so I'm going to use that for no other reason. So 0.26 is those executives who prefer trucks. The Q would be 1 minus, and that's going to be 0.74. Now we have to go back and say, well, how many actually were executives? And that was 160. So our sample size, the subset that we are looking at, is 160. In words, what is my random variable x? Well, x would be the number of successes where the executive prefers a truck. So this is the executive who prefers a truck, where P prime would be the percentage of executives in the sample who prefer trucks. The distribution I'm going to use is a normal distribution, and it's going to be 0.026 because that's going to be my mean. And then my standard deviation will be calculated as P, which is 0.026, multiplied by my Q, which is 0.74, and then divide that by my sample size of 160. So that would be the normal distribution that I would be using. If I were asked to draw the sketch and calculate the error bound, and also, I don't know why, I just really like the newborn elephants. This is in reference to the number of executives who prefer trucks. My mean would be 0.26. So this is 0.26. My EBM, which I'll show you how, or my EBP, excuse me, my EBP, I will show you how I got that, is going to be 0.0707. That means my lower end here is going to be 0.1942, and my upper end is going to be 0.33068. So this is the area that I'm looking at. My interval then is 0.1942 and 0.33068. So that's my confidence interval. The sentence that would go along with this is we are 95% confident that the number of executives who prefer to drive a truck is between 19.43% and 33.01%. Now, if I want to lower my sampling error, one of the ways I can do that is increase my sample size. The other way I can do that is to widen my confidence interval. So I can go to a 99% confidence interval, and that also will lower my sampling error. So then the last thing here is the sampling error was given as a survey plus or minus 2%. What does this mean? That means a sampling error that the true mean, it can be 2% above or below the sample mean. So that's what that means. Here is the spreadsheet I would recommend that you use. The confidence level again, my alpha, all of this stuff. None of this is anything different we haven't already seen. So my SQ, so my error bound, this is my Z alpha divided by 2. Again, I'm not going to take Z alpha and divide that answer by 2. This is just the notation of that. And then I'm going to multiply by the square root of P prime Q prime divided by N. This is my standard sample deviation, my NPQs, confidence level, my X. Now, this is the only thing that's slightly different. So if they give you as like 57 out of 195 and they don't give you at a P hat, you can put over here to the side like we did in chapter 7, the calculator, so you can just plug this in, or you can add these extra things, which is 57. This is out of 195, which also happens to be 195, and then this calculates my P hat. If they give this to me as a percent, say 57%, and they tell me it's 195 people, then I would put 57, and when I put 100 right here, and then that will calculate this X divided by my denominator, which then doesn't actually take into account this N. So really what that is X divided by the denominator, to make sure that I get the right percentage. My Q hat is 1 minus my P hat, confidence level. My alpha is 1 minus the confidence level. Alpha divided by 2 is literally that value divided by 2. And then I do the norm dot invert alpha. I could have done the norm dot S dot invert because I don't need to have the 0 and 1. I could just use the norm dot S dot invert. Again, I'm going to do the absolute value because you can see the z-score is to the left, and that's kind of expected. And then I have my upper and lower, and then this is checking to make sure that I can actually use that calculator. Now, the other thing that we're going to talk about really briefly is the +4. What the +4 does is it helps adjust for any errors that you get. So this +4 means that the sample size becomes 4 and the count for success becomes added 2. So that just gives us a little bit of margin of error play so that we're more confident of where it is. Desired confidence level usually is at least 90%. So how does that change stuff here? Well, so a random sample of 65, that means up here our N becomes 4 more, so it'll be 69. So this will be 69. And then the 31 students declared a major, use a +4. So that means to find my P hat, this is going to be 33 because I'm going to add 2 to success, and I'm going to divide by 69 because I have to add 4 to the count. And then, of course, I would find my P and my Q. What does the X represent in this? Well, the capital X is the number of successes where freshmen have declared a major. Capital P prime is a percentage of students who have declared a major. Now, the distribution I'm going to be using is a normal distribution. I'm going to be putting in my probability of success, which was 0.0478. And then my standard deviation would be the square root of 0.478 multiplied by my failure, which is 0.522, and then divided by that 69. So that's what that would look like. Oh, don't forget your parenthesis. 95% confidence interval, what would it look like? Well, since I know that my mean is 0.478, I found my EBP to be 0.126. That means I'm going to go down to 0.354 and I'm going to go up to 0.602. This is the region I'm looking at. So my confidence interval is going to go from 0.354 to 0.602. What does this mean? So we are 95% confident that the number of freshmen who have declared a major is between 35.4% and 60.2%. If you are needing to calculate the sample size, and we are in the land of proportions, what we know is that we're going to take this formula and rearrange it. When we rearrange it, we get this formula, which is n is equal to, I'm going to take my z-score and square it. I'm going to multiply it by my p hat and my q hat, or p prime and q prime, and then I'm going to divide that answer by my EBP squared. So determine the percentage of customers who click on ads. They want a 95% confidence, and so within 5 percentage points. Okay, so what happens? They didn't tell us what our proportion is. So if they don't tell us the proportion, the safe thing to say in this case is we are going to let my EBP, so we're going to let my EBP be 0.05 because I have a 95% confidence. So that is, 90% confidence. So that is going to be my confidence level. That means my alpha divided by 2 is going to be 1 minus 0.9 divided by 2. This gives me 0.05. And we're going to call this my EBP. EBP. Now, they don't give us our P. They don't give us our Q. So the safe thing to do is assume that P prime is going to be 0.5. That means Q prime is going to be 0.5. They don't give us that. That is the safe thing to use. So then my n is going to be my negative 1.645, the quantity square that comes from my z-score. I'm going to multiply that by 0.5, and then another 0.5, and then I'm going to take and divide that entire thing by 0.05, the quantity squared, and I end up with 271 is my sample size. Here is what I would have. So my confidence level, my P hat, my Q hat gets calculated. My EBP gets calculated based on this. And then I find my alpha divided by 2, norm dot invert. Again, this is, I'm not taking alpha divided by 2. This is alpha divided by 2. That's this cell that goes in there. Or you can use the norm.s.invert and you just put in the alpha divided by 2. And then here's my formula, which is P prime, Q prime, the z-score divided by EBP. Both of those are squared, so I just put them squared and I grabbed all the things that are appropriate. And that's it for this video.